let C be any contour from 1 to 1 plus I. So here's 1, and here's 1 plus I. So maybe like a straight line, that would be an example. Let C be any contour from 1 to 1 plus I that does not cross the negative axis or go through the origin. We want to compute the integral along the contour of 1 over z dz. And to solve this problem, we will use the fundamental theorem of calculus in the complex case. So suppose we have a contour z that has an initial point and a terminal point, z1 and z2. If the function f is analytic along the curve, and if capital F is an antiderivative of little f along the curve, then the integral of little f is simply big F of the terminal point minus big F of the initial point. So this should remind us very much of the fundamental theorem of calculus in the real case. The A to B here represent the interval from A to B, so we have a contour, a line segment from A to B, initial point A, terminal point B, f of the terminal point minus f of the initial point. So that's what we have here. Now the function 1 over z is analytic everywhere except at the origin. So as long as our contour does not go through the origin, then our hypothesis about f being analytic along the curve is satisfied. Now what about an antiderivative? The derivative of the principal branch of the logarithm is 1 over z. So log z is our antiderivative. There's capital F. And the antiderivative has to exist along the contour as well. And as long as the contour doesn't go through the origin or cross the negative real axis, then the log of z is defined, and its derivative is 1 over z. Recall that the principal branch of the logarithm function is not defined. It's not analytic, I should say, on the negative axis. It has a discontinuity, a jump discontinuity along the negative real axis, and it's not defined at the origin. So those points have been carefully excluded in the statement of the problem. The contour does not cross the negative axis or go through the origin. So that means then that the integral of 1 over z along any contour that satisfies those conditions is equal to capital F of 1 plus I minus capital F of 1. So that would be the principal log of 1 plus I minus the principal log of 1. And let's flesh these out. The log of 1 plus I is equal to the natural log of the modulus of 1 plus I times the principal argument of 1 plus I. The principal argument is always between negative pi and pi, and this should be a strict inequality here. So the natural log of 1 plus I, modulus of 1 plus I is the square root of 2. So the natural log of the square root of 2 plus I times the principal argument of 1 plus I. This number is on the line y equals x, so that angle is 45 degrees. So that's pi over 4. So there's the log of 1 plus I. And then the log of 1 is the natural log of the modulus of 1 plus I times the principal argument of 1. And the principal argument of 1 is 0. And the natural log of 1 is also 0. So this is 0 plus I times 0, which is just 0. So this one is 0. And our final answer is the log of the square root of 2, which is also 1/2 log 2, plus I times pi over 4, or pi I over 4. So there's the value of our integral using the complex version of the fundamental theorem of calculus.